Hey guys, Lissandro here, and today I want to focus on a special tutorial. I know I haven't done a tutorial in quite a while, and especially on electrical engineering. Mainly I've been busy with other stuff, and I've been doing other types of videos, and if anything, I've been doing software based tutorials like C++, Java, and so on. But today I want to do for the first time in a while, I want to do an electrical engineering tutorial. So I thought about it, and lately I've been talking with a good friend of mine. She's interested in LEDs, micro LEDs. So I thought about it, and I said, why not start with LEDs? But before I can get to LEDs, I need to explain what diodes are, and that's specifically what this video is about. I'm going to explain what a diode is. So without further ado, let's get right into it. So what is a diode? A diode is defined as, and it states, in electronics, a diode is a two-terminal electronic component that conducts primarily in one direction, asymmetric conductance. It has low, ideally zero, resistance to the current in one direction and high, ideally infinite resistance in the other. A semiconductor diode is the most common type today. It's a crystalline piece of semiconductor material with a P and N junction connected to two electronic terminals. Now let's take a look at the diagram again. As you can see here, this is what they were referring to, the P and N junction. And let me get to explaining what these P and N junction are. But first, let me explain what a diode does and what it is used for in its multiple applications. You see, in electronics, there are situations in which you cannot have current flowing back, that you only want current to flow only in one direction. When that is the case, you apply a diode in your circuit. And what it does is that it only allows current to flow in one direction and prevents it from flowing back. But what you might ask, doesn't current flow in one direction already? Why would you want something like that? In what case would you want something like that? And are there cases in which current flows back? Yes, there is. And it's found in something that we use almost every day, AC current. AC current, unlike DC current, alternates its current direction flow back and forth within a given time frame that we measured in hertz in the form of frequency. One of the most common frequencies being 60 hertz, which is the frequency used in the AC power outlets that we use. So now that I covered that, how would you use a diode, or what application could you give it in this case? And the answer is very simple. Ever wonder how your cell phone charges its battery from the wall power adapter? It converts AC current to DC current, and one of the vital and most important components that it uses to convert AC current to DC current is none other than a special type of diode known as a rectifier diode. I covered this in another video. I'll have a link in this card, in the description, and at the end of the video. But getting back to the point, what I showed you is one of the many types of diodes. In fact, it is one of the most common ones of its type. There are multiple types of diodes. You have LEDs, rectifier diodes, Zener diodes, Schottky diodes, etc., in varying ratings and capacities, each for varying purposes, functionalities, and applications. But in the general sense, what a diode does is similar to a one-way valve, which lets gas or liquid flow in one direction only. Let me briefly show you what a diode does under AC current. Okay, so what I have here is an AC power source. It's 120 volts. Later on I'll explain what RMS is. And as you can see here, it's 60 hertz, just your typical outlet power source. Now, let me explain briefly what 60 hertz is, just to give you a much more in-depth concept of what hertz is. It's pretty much the amount of times it alternates from positive to negative back and forth within a given time frame. It's usually seconds. So it changes, or better yet said, it completes 60 cycles within 1 second. So that said, let me show you. Okay, so as you can see here, it's going from 0 to positive to 0 to negative, and it keeps going. From here to here, from 0 to peak, whichever peak is 120. From 0 to the opposite peak is 120. Okay, so don't mind this. This is I'll explain later on what this is. This has to do with RMS. Okay, and if you see here 0 degrees, that's like a phase change. I'll also explain what that is anyway, but this is something brief that I wanted to cover. In reality, I already covered it in another video. The video I mentioned that I was going to put the link at the end of the video, or the card judges, or in the description. But anyway, let me show you what happens when you put in a diode. Okay, now I'm gonna put a virtual diode because it has the ideal properties. Okay, so if you just put in one diode, let me show you what happens. As you can see here, it's the same peak. However, it decreases, and that's because there's opposition in the opposite direction. However, it's not rectifying completely. And why? Because you have this here. So a little bit leaks out. A little bit of the power leaks through. That's why you don't see, what do you call it, on power adapters. They don't use one diode. They usually use 2 diodes, or the most common case, they use like up to 4 diodes to create what they call a full bridge rectifier. It's all in the video that I left in the description. But anyway, and let me go ahead and put yet another diode. Okay, close. Okay. I think this is, I'm not sure. Okay, hold on, let me connect the ground. Okay, now as you can see here, now it's in one direction. Now it converted it to direct current. As you can see here, the positive half of the cycle, it goes up to peak, goes down, and usually it will go down to the negative region. However, because the diodes are preventing from current from flowing back, it just stays at 0. So in this case, like I explained in the other video that I did some time back in regard to rectifiers, if you were to touch the circuit at this 0 region, you would not get shocked. Unfortunately, this is way too fast for you to touch it, but without getting shocked and everything. But as you can see, there's it's rectifying. Now, if I were to put like what they call a full bridge rectifier, you would see like multiple ripples, and it would be more consistent. You wouldn't have what they call a trickling power source. And sometimes this type of current is necessary. For example, there are batteries in which you require to charge and you require for it to charge and cool down. Why? Because when there are certain batteries that when you're charging them, they tend to overheat. And because of that, if you continue, you'll end up damaging the battery, or in the worst case, you'll end up making it overheat and catch on fire, like for example, lithium ion batteries or nickel cadmium batteries. So what happens in trickle charging, it charges. It charges as soon as it starts to overheat. And the power goes down, it cools down, it charges, and it doesn't let it overheat, and it allows it to actually charge. There's some batteries that you can't charge it like uniformly, continuously, like your regular direct current. You need trickle charge. But anyway, and that's pretty much it in regard to it. So let me get back to the other aspect of these diodes. So now let's get back to the P and N junction that I mentioned earlier. So what's with that? The reason why diodes have a P and N junction is because diodes are prepared in such a way that they are comprised of two halves of the same material, or sometimes different materials that have opposite charge, one half being negative charge and the other being positive charge. Now you may be wondering, how do they do that? And the way they do it is by getting semiconductor materials such as silicon or germanium in their intrinsic state and doping them. Doping is the process in which you get a semiconductor material in its intrinsic state and use what they call a dopant or doping agent to infuse it with impurities at a very low concentration to obtain desired charge polarity and or properties. Generally, dopants or doping agents infuse impurities consisting of antimony, phosphorus, and arsenic to obtain negative charge, and infuse impurities consisting of boron, aluminum, and gallium to obtain positive charge. The point is that when they manufacture both halves of the diodes of the opposite charge in such a way that both halves come into contact, they create what is known as a P and N junction, as a result creating what they call a depleted region, a zero charge region between the positive half, which is the P region, and the negative half, which is the N region. Normally, this region only expands so far due to the fact that because the depleted region is dielectric, like electrical insulators tend to be, the more the depleted region expands, the more the electrical potential between the P and N junction across the depleted region lessens, and at the same time, fewer positive and negative charges. When you connect a conventional current flowing from the P region to the N region, which is known as forward bias, the depleted region decreases because the current supplies more holes or positive charge on the P region and more electrons or negative charge on the N region to counteract the neutralization in the P and N region, which would otherwise be present due to the lack of holes in the P region and electrons in the N region when current is not present. As a result, this allows current to flow, and there is a voltage drop across the diode of approximately 0.7 volts, which is also the minimum voltage required for current to flow. Now, if you reverse the current in the opposite direction, which is known as reverse bias, what happens is that it further expands the depleted region in the P and N junction. The reason it does this is because electrons being supplied to the P region and holes to the N region. What this does is that it depletes the remaining positive and negative charges on either side, further expanding the depleted region and completely blocking the current flow. Now, there are some things to be considered. To start, every diode, like other electronic components, have a power rating. Too much power can burn out and damage the diode. Also, even though reverse bias blocks current flow, there is one exception. Depending on the rating of the diode, if the power you are applying in reverse bias is too high, it gets to what they call a breakdown, in which the electrical potential in reverse overcomes the depleted region. No matter if the entire diode is depleted, the result is that the diode shorts. Here's a graph of the diode in forward bias and reverse bias. So as you can see here, you can instantly tell that once you get to 0.7 volts, current will start to flow through the diode if it's forward bias. If you look at reverse bias, you can tell that it's reluctant to let current flow, even though there's a certain amount of current flow that leaks through, which is referred to as phantom current, which is negligible but is still present. That's of course until you get to what they call breakdown region, in which you essentially not only short the diode but essentially damage it. So anyway guys, before I bring this video to a conclusion, I just want to say this. There are a variety of different types of diodes. It's not just the type of diode I mentioned here. Each one has its own ratings, applications, different materials, different functionalities, and the list goes on. So what this video was mainly about is pretty much a brief description of what a diode is, how it functions, how it's manufactured, even though I did give a little bit more detail than usual. But anyway guys, I hope y'all enjoyed this video. Go ahead and please like, share with friends or whatever. Oh, and don't forget to pledge to my Patreon. But anyway guys, thank you guys for watching, and I'll catch you guys next time.